Welcome to how to make a chess program in Go, and this I plan to make this included in the previous video, but that was too much. It's not video number 20, but let's call it video number 20B then. We left with last time with this principal variation list. A slice to keep principal variations and some methods about that. Let's go on with the real AlphaBeta. So we can start at the root. We have our PV list, and we need a child PV. Each child need to keep their principal variation like this. I think we need to clear it, but first we need a new, and we don't have this, so we need to write that. Let's find the object. Here we can copy this add and make a new from that, and we just have a make like this. I hope that when I use capacity, max apply as capacity, it will make the garbage collection to keep its hands off our PV lists. I don't know, but I hope so. Okay, so move list. We do the same with move list. It's a make of capacity 60. It should be enough. And we can remove this. We don't need that, but we have a limit start time to measure the time, and we set that to now. In fact, we need another time mark. We can call that next time, because we need to break the search now and then and see if its time is out. It will be clear when we come to those parts. It's also time now. We need to define these two. It's here. So we have the start time. It's of type time. Why it changed to lowercase? It should be uppercase, like that. And next time. Like so. Okay. And we have an alpha and a beta, and they are initialized to minimum evaluation, maximum evaluation to start with. And the best move and the best score initialized. And depth. And we will count the nodes and clear the move list. Okay, we can change this slope a bit. So we just loop through the move list and have an index. And I don't know if we need the address to each move or not. We will see. We will find out. And we need to clear the child PV, and we will tell the GUI what move we are searching right now. That's a good idea. And here is the AlphaBeta function. So we search, we send down beta, alpha, the depth -1 and the ply +1. That's how we will do on each level. We can use 1 here, in fact. Okay, this is the thing I talked about. In order to maximize on each ply, we send down -beta and -alpha, and we switch the place between the two. So on ply 1 they will use -beta as their alpha. And when we get back to score, we negate it. We maximize on every level. If score is greater than best score, then we clear our PV. There are some stars and colon to put in here. Okay. Okay, so the best score is the new score. So, and we can we have a new PV, child PV. We use the child. Now we have a new best child, and we use that PV. Best move is the current move, and alpha is score. And remember that best score, at least in the beginning, can be updated without alpha is updated. We have a new best move, so we have good news to the GUI. So we tell the GUI about, we make a string with sprintf info score, the CP, the depth, nodes, and principal variation. That is best score and depth, and count nodes. And this is our string of PV. We can copy down that, so use the same down here, but we cannot use, we use the best move evaluation like this. That was the root. Now we can go down to the search. First of all, let's count the nodes. And we will return evaluate if depth is equal to 0. Like this. And we receive alpha, beta, depth, ply, and our new PV list, like so. And in the end we return best score. And we also need to clear our PV, and we make a new move list on each node. So move list is capacity 60. That doesn't mean, capacity 60 doesn't mean that is the maximum value. If we get more than 60 moves, if we have more than 60 moves, Go will, I think, double capacity and reallocate the whole move list somewhere else. And then garbage collection will have some work to do. I hope and I think that if we do not exceed 60, Go will allocate the move list on the same place on the stack, and it will not be moved anywhere. until the function is finished, and then it will disappear with the stack data. If 60 is an upper limit, I'm not sure. I think so. I think it will never or almost never happen that 60 is exceeded. That is, of course, something that can be measured later on. So we keep the old generate and sort moves until we have a better one. Best move, best score, initialized, like this. So we will have a child PV list for this node. So, and we will go through all the moves in the move list. We look at each move, we clear the child PV and make the move. So, and our AlphaBeta function, we call ourselves one ply down, minus beta minus alpha, depth minus 1, ply plus 1, and the child PV for the children to work on. And I need to change in the root as well. I forgot that child PV here. Okay. So, and then we unmove. And if score greater than best score, okay, update best score. And we have a new PV. And we put our move first and the child PV under below. So if score greater than or equal beta, we have a beta cutoff, GP, and we just return the score and save a lot of time. If score not greater than beta but greater than alpha, then we have a new best move. Can do like this, and a new alpha. We can update the alpha. If time since last time, that is next time, maybe it should be last time. Okay, if it's greater than time duration 1 second, we will tell the GUI something. And we have the start time that we can send to the GUI. Wait. I need to think about this. I really need to think about this. It doesn't look really good. First of all, I'm not sure that this time functions in Go are efficient or not. So instead of using timing like this, we could count the nodes and say every 10,000 nodes or something, we break and check if it's time to send something to the GUI. And also 1 second is it's not good enough to see if, when we start to use the time, like move time or time per game or something like that, we need to check more often than every second. But I think I'll stop here and come back with some clever conclusions. And here comes my final decision. I'll keep the Go timing for now, until later. I also keep this break every second, because every second we will write something to the GUI. Later on, when we implement the move time or time per game, we can change this. And during profiling and optimization, we can see if this time functions are good enough. So if the GUI tells us to stop, we stop by returning alpha. Something is wrong with T1 up there, and that's because time since is a duration type of duration, and they don't have second. They don't have milliseconds, so I need to fix that. Dividing by 1000 by hand is the solution, of course. Now we have reached the sad time to say goodbye and see you next time.